Usually when you sit down to a meal, there's just this expectation of simplicity.
Yeah, for sure. You don't really overthink it.
Exactly. You look at a bowl of dal or, a plate of rice and lentils, and it just feels grounding. It's basic.
Right.
But then if you step into the actual world of industrial food processing, suddenly that simple bowl of food reveals itself to be the product of this invisible high-stakes battleground.
It really is a battleground.
Right. I mean, we are looking at a landscape that is fundamentally a massive kinetic war zone. And that is literally what puts the food on your table.
Yeah, we tend to think of our food supply chain as this, gentle pastoral system. Farmers and fields.
Just a nice tractor driving along.
Exactly. But the reality of getting a single pigeon pea from a field to your dinner plate, it involves an incredibly unforgiving mechanical environment.
Unforgiving is a good word for it.
I mean, the margins for error are microscopic, and the physical forces involved are just immense.
And that reality is the focus of our deep dive today. We're pulling data from this fascinating stack of documents. We've got technical papers from engineering journals, places like IGEST and IJSORT, that detail the granular mechanics of pulse milling.
Right, the real heavy engineering side of things.
Yeah. And alongside that, we have industry articles from Miller Magazine and this really deeply philosophical piece on systems thinking by an author known as The Quiet Architect.
Which is such a great piece.
It's incredible. So our mission today is to unpack a hidden industrial choke point. We're going to explore the critical difference between preventive and predictive maintenance in milling.
And this isn't just about fixing wrenches and bolts?
No, not at all. It's about how the shift from manual checklists to data-driven edge AI systems is saving millions of tons of food from just literally turning into useless dust.
Yeah, and it also happens to be saving the profit margins of these factories in the process.
For sure.
Because the transition we are talking about fundamentally alters the lifespan of the machinery itself and the overall productivity of the entire plant.
So to set the baseline for all of this, we need to introduce a concept from the research that sounds like it belongs in an advanced physics seminar.
Oh, yeah.
But it actually dictates the economics of food production globally. It's called the Rotary Kinetic Deficit.
The Rotary Kinetic Deficit. It's a term that perfectly captures the razor-thin margins of the physical world.
That sounds so sci-fi.
It does. But to understand why a deficit in kinetic energy even matters here, we first need to look at the reality of dal milling.
Right. So what do we actually talk about when we say dal milling?
Well, we're talking about the industrial process of cleaning, dehusking, and splitting raw agricultural pulses.
So things like pigeon peas, green gram, black gram.
Exactly. The goal is to transform that raw seed into the recognizable clean halves that you actually cook and eat.
Which basically means removing the outer shell, the husk.
Yeah. And the star of this entire operation, the absolute center of gravity in a pulse mill, is a machine called the emery roll dehusker.
And I think we need to give a sense of the sheer physical forces at play here. Because this isn't just some gentle kitchen appliance you have on your counter.
Oh, no, not even close.
We are talking about a massive, heavy-duty piece of machinery. It's built around this cylindrical, abrasive carborundum roller.
And let's unpack the physics of that roller for a second, because carborundum, for context, is silicon carbide.
Okay, so what does that mean in practical terms?
It means it is an extremely hard synthetic compound. It's actually often used in bulletproof vests and high-end automotive brakes.
Wait, really? Bulletproof vests?
Yeah. It is incredibly abrasive and durable. And the sources note that this massive stone and steel cylinder inside the mill is often running at 2,400 to 2,700 revolutions per minute.
That is, when you translate that rotational speed to the actual surface of the roller, it means the abrasive stone is traveling at 13.5 to 14 meters per second.
Just flying.
Imagine a wall of sandpaper flying past your face at 13 meters per second.
It's a violent environment.
And the mechanics of dehusking rely entirely on this violent speed.
Right.
Like the pulses are fed into the machine and forced into this very tight gap between that spinning abrasive roller and a metal sieve or screen that surrounds it.
Right. And the friction inside that gap is what tears the outer husk right off the pulse.
It just rips it right off.
Exactly. That gap is the crucible of the entire factory. Because from the outside, a dal mill looks like a straightforward operation,
Sure, grains go in, dal comes out.
Yeah, grains are poured into a hopper, husks are stripped away, split peas pour out the bottom. Simple. But the engineering papers we're looking at point out that it is actually a high-friction, low-margin balancing act.
Because the whole system is built on physical resistance.
Yes, the profit of the factory is the direct byproduct of uniform mechanical resistance.
So uniformity has to be like the absolute key here, right? Because
Yeah.
if that gap is fixed,
Exactly.
then the grains going into it need to be perfectly sized.
Yeah. And that is the core vulnerability of the system. The deficit happens when that uniformity breaks down.
Okay, so how does it break down?
Well, before the pulses even reach that violent emery roller, they have to pass through a grading machine.
Oh, so they get sorted first.
Right. The grader's job is to sort the raw agricultural products so that only grains of the exact same size enter the dehusking chamber at any given moment.
Got it. So it groups all the small ones together, all the medium ones together.
Exactly. But if that grading machine fails to isolate those uniform sizes, the entire dehusking system collapses into chaos.
Okay, let's visualize that for a second. You have a fixed gap between a spinning stone and a metal screen.
Oh.
If the grader fails, you have small grains and large grains entering that fixed gap together at the same time.
And when that happens, the chamber instantly experiences asymmetric pressure.
Meaning uneven pressure.
Right. The small grains are too little to be caught by the friction of the stone, so they just slip right through the gap.
They completely escape the abrasive action.
Yeah, they come out the other side, keeping their husks completely attached. They're totally unprocessed.
Which is bad for business.
It's a waste of a pass. But the large grains face the opposite problem, which is much worse. Because they take up more space in that fixed gap, they take the full, devastating brunt of that 2,700 RPM roller.
Oh, wow. Because they're too big for the space.
Exactly. They're subjected to immense, disproportionate pressure.
So they just get crushed.
They shatter. The valuable pulse cotyledons, the actual fleshy interior of the pea that the factory intends to sell, they are completely destroyed.
It just turns into dust.
The product literally turns to powder. The research notes that in traditional setups, factories experience a 5 to 15% loss of product just to broken and powdered grains.
A 5 to 15% loss.
Yeah.
I mean, when you think about the scale of global food production, losing up to 15% of your total yield to dust is just a catastrophic inefficiency.
It's a staggering volume of human food being turned into dust simply because of asymmetric physical friction.
I want to relate this to something we deal with every day, right?
Yeah.
Because industrial milling can feel abstract. Think about the alignment on your car's tires.
Okay.
If your car's alignment is off by just a fraction of a degree, your car still drives. You probably won't even notice it on your daily commute.
Right, it feels fine.
But over the course of several months, your tires wear out unevenly, and you eventually have to replace them. It's a slow, progressive bleed on your wallet.
Yeah, that makes sense.
But in a dowel mill, if this massive abrasive roller, or the grading sieve feeding it, is off by a fraction of a millimeter, your product isn't slowly damaged over months.
No, it happens instantly.
It is instantly destroyed the absolute second it touches the stone. The margin for error is essentially zero.
That comparison really highlights the unforgiving nature of industrial hardware. Because, in software development, if there is a bug or an alignment issue in the code, you just patch it.
Right. The user refreshes the page and it's fixed.
Exactly. But in hardware, and specifically in heavy industrial kinetics like pulse milling, failures are violent and immediate. When machinery misaligns, the mill experiences what the industry calls unscheduled breakdown maintenance.
Meaning the operation just forcefully stops.
Yes, everything grinds to a halt.
So if a fractional millimeter of misalignment turns thousands of dollars of profit into powder, how on earth do factory managers keep these roaring heavy-duty machines perfectly calibrated?
Well, to understand the modern solution, we really have to look at the historical evolution of maintenance.
We have to look at the old school methodologies.
Right. To appreciate where the industry is moving, we have to look at how factories have historically dealt with this harsh physical reality.
Right.
And the baseline approach, which is just the absolute worst case scenario for productivity, is unscheduled maintenance. Sometimes they call it corrective or breakdown maintenance.
That basically means running a machine until it physically breaks or explodes and then frantically scrambling to fix it.
It is the very definition of reactive management. You just run the emery roller until the bearings literally seize up and then you panic.
Which sounds incredibly stressful.
It is. The sources highlight a phrase regarding this that I think is so telling. The most expensive phrase in manufacturing is unscheduled maintenance.
Wow. The most expensive phrase.
Because if you picture the factory floor when this happens, the impact is immediate. The entire production line stops. The heavy machinery is dead quiet.
Right.
You have laborers just standing around with nothing to do. You are still paying their hourly wages. You're still paying for the electrical overhead, the facility overhead, but absolutely zero product is moving out the door.
The profit margins just instantly vanish.
They evaporate.
Not to mention the collateral damage, right? Because if a heavy steel bearing explodes at 2,700 RPM, it doesn't just quietly stop working.
Oh no, it's
It
violent.
sends shrapnel through the machine housing. It can physically bend the main drive shaft. So you aren't just replacing a $50 bearing anymore.
Right, you're rebuilding a $10,000 piece of machinery.
Like-
And that collateral damage is exactly why smart operators realized decades ago that running equipment until it breaks is just an unsustainable business model.
You just can't survive doing that.
No. So the industry evolved to the next level, which is scheduled or preventive maintenance.
Okay, preventive maintenance.
Professor Dr. Farhan Alfin, he's the food engineering department head at Eurasia University. He wrote a really detailed piece in Miller magazine breaking down the specific methodology.
And what did he find?
He explains that preventive maintenance is the traditional time-based approach to machine health.
Okay, so this is the era of the daily, weekly, and long-term checklists.
Exactly. It's based strictly on the manufacturer's operational specifications.
Right, so a maintenance technician basically goes out onto the floor with a literal or maybe digital clipboard.
Yep, a clipboard and a schedule.
They do periodic cleaning, they check the tension of the drive belts, they perform regular oil changes, and they conduct these visual inspections of the moving parts to ensure the machine will hit its expected lifespan.
That's the idea, yeah.
And, I mean, on the surface, that sounds like an incredibly responsible way to run a factory.
It definitely appears responsible. But when we connect this to the broader picture of factory economics and machine lifespan, preventive maintenance is actually fundamentally flawed.
Flawed how?
The reason it falls short is that it relies almost entirely on rigid, arbitrary timelines and human visual inspection.
Okay, wait, let me push back on that for a second.
Sure.
Let's say I take my car to the mechanic every single Tuesday.
Okay.
Every Tuesday, whether the engine is making a weird noise or not, I take it in and I pay the mechanic for an hour of their time to put it on the lift and look it over.
Right.
Isn't being overly cautious with preventive maintenance vastly superior to waiting for my transmission to drop out on the highway?
Yeah.
Why is a structured checklist considered a bottleneck for a modern mill?
That is the exact paradox that plant managers have wrestled with for decades.
It seems like a tough call.
It is, yes. Taking your car in every Tuesday will likely prevent a highway blowout. But consider the operational cost of doing that.
All right, it gets expensive.
And it's not just the mechanic's hourly fee. It's the loss of your vehicle every single Tuesday. You can't use it.
Oh, right. I'm taking the bus that day.
Exactly. Now, in a factory setting, to check the inner workings of an emery roll machine-like, to inspect a bearing or measure the tension of a drive belt safely, you cannot do it while the machine is running at full load.
Obviously not. That would be incredibly dangerous.
Right. You have to stop the machine. You have to shut down production completely.
You have to follow strict lockout, tag-out safety procedures. You have to wait for the massive stones to stop spinning. Wait for the dust to clear in the room.
All of which takes hours.
Wow.
So stopping perfectly healthy machines just to perform unnecessary maintenance checks, it causes massive production losses.
You are literally turning off your profit engine to see if it might be broken.
Exactly. Furthermore, you are incurring high labor costs for the maintenance technicians who are performing these arbitrary checks.
That makes total sense.
But the deeper, more insidious flaw with preventive maintenance is what the quiet architect source describes as a lack of legibility.
Legibility.
Yeah.
Like trying to read a book that has been printed with invisible ink.
That's a perfect way to put it, because the human eye, no matter how trained or experienced the technician is, it cannot see the microscopic degradation of a ball bearing housing while the machine is turned off and sitting idle.
Right, because when it's off, it just looks like a solid piece of metal.
Exactly. A technician can look at a steel shaft, check the box on the clipboard, and say it looks perfectly fine, but inside that metal lattice, microfractures are forming.
Oh, wow.
The industrial lubricant might be failing at a microscopic chemical level that you just can't see.
So they miss it entirely.
Right. The technician signs off on the checklist, turns the machine back on, and 2 days later, that same bearing tears itself apart under load.
Because it only fails when the pressure is applied.
Yes. Preventive maintenance is fundamentally blind to the actual, real-time physical health of the machinery.
So the factory's basically stuck between a rock and a hard place.
Pretty much.
They either run the machinery until it explodes and suffer unscheduled downtime,
Right.
or they stop the machinery constantly just to look at it, suffer scheduled downtime, and still miss the microscopic problems because human eyes can't see through steel.
That was the harsh reality for the entire manufacturing sector for a very long time, until the industry finally entered the data era.
Ah,
And this brings us to the critical difference between preventive maintenance and predictive maintenance.
predictive maintenance. This is where the evolution of the factory floor really
It's
accelerates.
a huge leap forward.
The research actually traces the formal introduction of predictive concepts back to Turkey in 1988. It was introduced by R. Kubilay Kozy as Kestirimshi Bakum at a National Machine Design and Manufacturing Congress.
Wow, 1988.
Yeah, and at the time, it was a radical departure from the whole clipboard methodology.
It represented a fundamental paradigm shift, because predictive maintenance is the shift from manual, human-driven monitoring to data-driven automated systems.
So how does that work in practice?
Instead of stopping the machine to look at it, the strategy is to measure its operational parameters while it is running.
While it's actually doing the milling.
Yes, under full load, actively doing its job.
So you let the machine continue making you money while you interrogate its health.
Exactly. You use non-destructive testing methods to gather data.
Like what kind of methods?
Well, the sources list several key techniques. Technicians might analyze the lubricating oil for microscopic metal shavings, which indicate internal wear.
Okay, that makes sense.
Or they use infrared thermography to see if a component is generating abnormal heat friction.
Just looking at the heat signatures?
Right. They also use ultrasonic testing. But crucially, for heavy kinetic machinery like an emery roller, the most vital metric is vibration measurement.
Vibration measurement, which leads us directly to the hardware described by the Quiet Architect,
Yes?
a system they call the Acoustic Yield Governor.
Such a great name.
It really is. And this is where Edge AI, which, just to clarify, is artificial intelligence processing data locally right on the machine, rather than sending it to a distant cloud server, bridges the gap between physical hardware and digital software.
Right. It's making the decisions locally.
Exactly. And the aesthetic described in the source paints a really vivid picture. Imagine this massive, brutal, steel-bearing housing on the emery roller. It's covered in thick pulse dust, it is violently shaking, the noise in the room is deafening,
Total chaos.
and bolted directly to that raw steel is a heavy-duty piezoelectric vibration sensor.
Just sitting right there in the middle of it all.
Yeah. The source describes it as having a matte black, Dieter Rams-style industrial design.
Very minimalist.
Minimalist, totally unassuming.
It is designed to be invisible,
Yeah.
to simply do its job in a really hostile environment. And that piezoelectric sensor doesn't hear sound waves in the air like a normal microphone would.
Oh, it doesn't?
No, it physically feels the mechanical stress and vibration of the metal it is actually bolted to.
That is wild.
And that sensor is wired into a local microcontroller, something like a Raspberry Pi compute module.
There's a tiny little computer.
Exactly. And it's housed in a rugged IP67 rated enclosure to protect it from all the dust and vibration. That little box acts as the local edge brain.
Okay, let me play devil's advocate on the hardware for a moment.
Go for it.
You are taking a highly sensitive, delicate piece of computing equipment, essentially a tiny artificial intelligence brain, and you are bolting it to a machine that vibrates so violently it strips the husks off thousands of seeds a minute.
Yeah, it sounds like a bad idea, right?
Doesn't the sensor just rattle itself to pieces? How is this fragile technology a better solution than a rugged maintenance worker with a clipboard?
That is a primary concern for any plant manager considering the upgrade. But the engineering behind these sensors accounts for the environment.
So they build them tough.
Extremely tough. That IP67 rating means it is entirely dust-tight and can survive being completely submerged in water.
Oh, wow.
The internal components are often encased in shock-absorbing resin, so nothing shakes loose. And honestly, the cost of replacing a damaged sensor, maybe a few $100s, is mathematically irrelevant compared to the cost of an unscheduled shutdown of a 50-ton-per-day milling line.
Right. The value of the data far outweighs the fragility of the hardware.
By a landslide.
And the magic here is really in the software architecture. Because the AI on that edge brain isn't connected to the cloud, it isn't pinging servers across the globe.
No, it's totally isolated.
It is trained on one extremely specific data set. the exact acoustic and vibrational baseline of a perfectly calibrated dehusking chamber.
And this is the core principle of acoustic governance.
How so?
Well, when that emery roller is perfectly aligned, when the gap between the stone and the sieve is exactly right down to the millimeter, and when the bearings are pristine, the machine vibrates at a very specific set of frequencies.
Like a signature.
Yes, it emits a distinct, healthy acoustic signature.
Think about a professional musician tuning guitar, right?
Okay.
Yeah. They don't wait for the string to snap in the middle of a concert. That would be unscheduled maintenance.
Total disaster.
And they don't stop the song every 5 seconds to blindly turn the tuning pegs just in case it might be out of tune. That would be preventive maintenance.
Right, that would ruin the show.
Exactly. What they do is they play the song, they listen to the pitch, and the absolute microsecond that the string goes flat, their ear catches the frequency shift. Yeah. And they make a micro adjustment on the fly without stopping the performance.
That analogy perfectly illustrates what the acoustic yield governor does. But of course, it operates at a frequency and speed far beyond human auditory capability.
Way faster than a musician.
Oh, yeah. When that abrasive roller starts to degrade, or when the grating sieve misaligns by even a fraction of a millimeter long before the pigeon peas actually start to fracture and turn to dust, the acoustic signature of the machine shifts.
The note goes flat.
Exactly. The vibration pattern changes, and the piezoelectric sensor feels that shift in real time. The edge brain compares the new vibration data to the perfect baseline, identifies the kinetic deficit warning, and instantly alerts the plant manager.
The source actually notes the system sends a daily SMS or WhatsApp summary.
It literally texts them.
It gives them a time to failure prediction and the exact percentage of the kinetic deficit. It literally texts the manager and says, the Tuesday night shift is currently burning margin because the grating sieve on machine 3 is loose.
It's giving a digital voice to the degrading hardware.
It's just incredible.
And the ability to continuously listen to the machinery fundamentally alters the economics of the entire factory. When you shift from manual monitoring to automated data-driven systems, the ripple effects across the plant's productivity are just immense.
We really have to look at the math of that ripple effect because the numbers in the engineering sources are staggering.
They really are.
When a facility moves to predictive maintenance, unscheduled breakdowns decrease by 35 to 45%.
Almost half.
Overall production levels go up by 20 to 25%. And maintenance downtime, the hours the machine is shut off for arbitrary checks drops by 25 to 30%.
It's a massive efficiency gain.
Overall, Professor Alpha notes that predictive maintenance is 8 to 12% more profitable than traditional preventive maintenance.
And to truly grasp what that 8 to 12% profitability actually looks like on the ground, we need to examine the math of the final product yield.
Okay, let's break it down.
The Quiet Architect source lays this out clearly. Imagine a medium-sized mill that processes 50 tons of raw pulses every single day.
50 tons. That is 50,000 kilograms of food moving through the facility every 24 hours.
That's a lot of material. So keeping that volume in mind, recall the rotary kinetic deficit we talked about.
Really?
If there is an undetected alignment issue, perhaps just a slight wobble in the abrasive roller that a human technician cannot see on their daily walkthrough, but the acoustic sensor can hear, and it causes just a 1% loss of product to powder.
I mean, a 1% loss sounds almost negligible on a spreadsheet.
It sounds totally negligible until you apply it to the actual volume.
Yeah.
1% of 50,000 kilograms is 500 kilograms.
Oh my God.
That mill is losing 500 kilograms of perfectly good agricultural product, pulverizing it into useless dust or like low-grade animal feed every single day.
Every single day. That's devastating.
By catching that kinetic deficit instantly through acoustic monitoring, the factory manager maintains proper machine calibration in real time. And this directly and immediately increases the final product yield.
So basically, by bolting a small black box to the bearing housing, the factory is saving half a ton of human food from being destroyed every 24 hours.
Exactly.
The source points out that the financial gravity of this for purchasing departments is immense. The return on investment for the factory manager is realized within a week. You could offer to install these sensors for free for 2 days, hand the plant manager a data report showing exactly how much margin they burned on a random Tuesday night shift due to micro vibrations, and they will buy the system immediately.
Oh, without question, the payback period is that obvious.
It really is.
It is not abstract technology, it is recovered yield. And the benefits of optimal calibration extend beyond just the sheer volume of food saved. It actually heavily impacts the aesthetic quality and the market value of the final product.
Right, because buyers pay a premium for how the doll looks in the bag at the grocery store.
Oh, aesthetics matter a lot. The sources detail how gentle polishing actions inside the mill provide a natural waxy coating and a shiny surface to the pulses.
Okay, so it makes them look appealing.
Yeah. But this polishing requires very specific low temperatures to maintain the chemical integrity of that waxy sheen.
Ah.
If the machine is vibrating violently, if it is misaligned even slightly, it generates excess physical friction, which translates to excess heat.
And heat is the enemy here.
Yes, that heat melts or ruins the waxy coating, destroying the shine. The market value of the batch plummets because it looks dull and overprocessed.
So it's incredible that a fractional millimeter of misalignment, completely invisible to the human eye, can quietly bleed hundreds of kilos of profit and ruin the aesthetic quality of the food simultaneously.
It's all connected.
This transition to predictive maintenance isn't just about saving wrenches and bolts from breaking. It is about maximizing the output of the global food supply and protecting the economic lifeblood of the milling business.
And as we zoom out from the mechanics of that single emery roller, we can see how this level of data-driven control scales up to automate the entire facility.
Right, it doesn't just stop at one machine.
No. This brings us to a broader shift discussed in the sources.
Oh.
The massive reduction in energy consumption, the lowering of labor costs, and a really profound philosophical concept regarding the role of technology on the factory floor.
The contrast between the older manual mills and the modern automated facilities is stark. The papers detail the architecture of a modern 130-ton-per-day Dell mill.
That is a massive operation.
We are talking about an incredibly complex, fully automated behemoth of a facility. A system of this scale utilizes roughly 170 individual electric motors, 180 automated slide gates to route the grain through pneumatic tubes, and 50 different level indicators just to manage the storage silos.
Just mind-boggling complexity. And the labor reduction enabled by this automation is immense.
How big of a difference are we talking?
Well, an older, non-automated plant processing, just 30 to 40 tons a day, traditionally required 15 laborers to run the system.
15 people.
Yeah. Those workers were manually handling the unloading, dragging bags across the floor, manually loading hoppers, and constantly monitoring the chaotic flow of grain to prevent jams.
It's very physical, dangerous work.
Extremely. But that massive 130-ton modern plant, with proper automation and predictive monitoring systems, the entire facility can be run by just 2 to 3 operators sitting in a control room.
Wow. From 15 down to 2 or 3. That is a massive reduction in direct labor overhead.
It is.
But it also results in a massive reduction in wasted energy, right?
Yes, absolutely.
Because in the older, manually operated plants, the engineering audits found that many machines were frequently left running idle without any product in them.
Right, because the workers couldn't keep up with the flow.
Yeah, so large motors were just spinning away, wasting thousands of dollars in electrical current.
Just burning money.
Predictive automation systems link the flow of the agricultural product directly to the power supply. If there is no grain detected in the chute, the machine automatically powers down.
And the automated monitoring also tackles energy waste on a deeper diagnostic level.
What do you mean by that?
Well, the sensors aren't just listening to acoustic vibrations. They are also continuously monitoring the electrical power draw of those 170 motors.
Oh, they're watching the electricity too.
Yes. The sources point out that measuring the motor draw amperage minute by minute is a highly effective predictive tool.
Okay, wait. How does electrical amperage predict a mechanical breakdown? That feels like 2 different languages.
It all comes down to friction.
Okay.
If a physical bearing is starting to seize up due to a lack of lubrication or microscopic wear, it creates more mechanical resistance on the drive shaft.
Right, it's harder to turn.
Exactly. So the electric motor has to work harder to overcome that new resistance just to maintain its required 2,700 RPM.
Oh, I see.
To work harder, the motor must draw more electrical current or amperage from the grid.
It pulls more juice.
Exactly. An automated system monitors that baseline current. It can predict a catastrophic bearing failure days in advance simply by spotting a steady, abnormal spike in power consumption on a specific motor.
That is brilliant. The physics of the failing metal translates into electrical data, which translates into a text message warning the operator.
It's all just data flow.
But I want to pause on the labor aspect for a second. Going from 15 workers wrestling with heavy bags of grain in a dusty room, to 2 operators sitting behind digital screens managing data flow.
Yeah.
This brings up a critical point made in the Quiet Architect source regarding a concept they call restorative engineering.
This is perhaps the most vital underlying philosophy in all the provided material.
I totally agree.
Because whenever the topic of factory automation is discussed, the immediate cultural reaction is fear of human replacement.
Right. People think, oh, the robots are coming for our jobs.
The assumption is that robots and AI are simply tools for mass layoffs. But the author of that source tells a very powerful anecdote that completely reframes the purpose of industrial technology.
I want to make sure we relay this story clearly because it honestly shifted how I view automation.
It's a great story.
The author recounts being on a factory floor several years ago, observing workers on an explosive assembly line.
Yeah.
These operators were physically handling live grenades, and the author notes that the workers were operating as if they were holding their breath.
Just absolute tension.
Fear was the primary operating mechanism dictating the workflow of the day.
It was a truly high-stakes, hazardous environment. And the engineering team in that facility didn't bring in an automated robot to be flashy or to seek a quick return on investment by cutting salaries.
Oh, no, that wasn't the goal.
They introduced a specific robotic arm, a TechMan cobot, which is a collaborative robot designed with sensors to work safely in the same physical space as humans.
Right.
They brought it in to physically absorb the risks of the explosives. They moved the human hands away from the blast radius.
And the author notes that the metric of success for that engineering project wasn't a spreadsheet showing capital savings.
Not at all.
The metric of success was the lead engineer receiving a text message from a floor worker that simply read, "I reached home safe tonight."
That outcome is the pure essence of restorative engineering.
It really is.
The philosophy posits that true technology must restore human capability, safety, and dignity. It must never act merely as a cheap, disposable substitute for a human operator.
Right.
The goal of automation should be to physically isolate humans from hazardous environments and elevate their daily function.
So imagine you are a worker in one of those older manual dowel mills. The mandate of restorative engineering applies just as much to milling pigeon peas as it does to assembling munitions.
Absolutely it does.
Because the old way of pulse milling relied entirely on human sweat and the constant fear of a breakdown. It forced humans to perform mundane, physically impossible tasks.
Like trying to visually inspect a microscopic fracture inside a steel bearing.
Exactly. Or breathing in thick agricultural dust for 12 hours a day while straining to listen for a machine to start rattling over the deafening noise of the factory.
It's degrading work. And predictive maintenance and edge AI acoustics aren't replacing human intelligence in that factory, they are augmenting it. These systems refuse simple replacement. By handling the dangerous microscopic monitoring, they move the human operator away from the physical danger of the spinning carborundum stones and the respiratory hazard of the dust.
They get him out of harm's way.
Yes. They elevate that human from a manual laborer to a position of intelligent governance. The human is no longer a pair of hands waiting for a heavy machine to explode.
They are the orchestrator.
Exactly. Responding to digital intelligence and making strategic decisions about plant flow.
It restores a sense of dignity and control to the factory floor. It is just a profoundly hopeful way to look at the implementation of industrial AI.
It really changes the narrative.
However, the research also points out a glaring caveat here.
Yeah.
You can have the smartest, most restorative AI sensors in the world bolted to your machines, and you can still suffer massive product losses if the physical building itself is working against you.
The environment matters.
Which brings us to the final major concept in the sources. Systematic layout planning, or SLP, which deals with the space around the machinery.
Because if we look at the entire operation as a holistic system, automation only solves specific bottlenecks. It doesn't erase all inefficiencies.
Right. It's not a magic wand.
Exactly. Predictive maintenance solves the problem of the machine's internal health. But what about the physical health of the factory layout itself?
The actual floor plan.
Yeah. The paper from the International Journal of Engineering, Applied Sciences and Technology dives deep into this specific vulnerability.
They conducted a case study on an existing dowel mill to identify and eliminate obstructions in the material flow.
And what they found was really interesting.
Yeah, they discovered that the actual physical architecture of the plant floor directly impacts how much product survives the milling process.
The building itself was hurting the yield.
Right. So they utilized systematic layout planning, or SLP, to completely redesign the floor plan. The first major result they achieved was shrinking the operational footprint. They reduced the total required space from 300 to 249 square feet down to 300 and 175 square feet.
And shrinking the footprint of a factory isn't just an exercise in saving money on real estate or heating costs.
No, it has a functional purpose.
In milling, the spatial layout dictates the physical journey of the pulse.
Right.
In the older, inefficient layout, the raw agricultural material had to travel through a convoluted maze of pneumatic pipes, vertical bucket elevators, and multiple routing chutes just to get from one machine to the next.
So why is distance an enemy to a pigeon pea?
Because every inch of travel involves kinetic friction. Every time a fragile pulse is sucked through a long pneumatic pipe, dropped down a steep metal chute, or forced around a sharp 90-degree elbow joint in the tubing, it takes physical damage.
It gets knocked around.
It collides with the walls and with other seats.
The product is essentially getting beaten up just trying to navigate the building.
Exactly. The researchers noted that in the older layout, because of inefficient routing paths, the pulses were sometimes forced to pass through the abrasive stone rollers twice just to get to the next sorting stage.
Wow. Double the torture.
Yeah, completely unnecessary. By utilizing SLP algorithms to map the heaviest volumes of material flow, they altered the equipment positions to ensure the most direct, shortest path possible.
Draining the maze.
Exactly. They ensured a single, highly efficient pass through the stone roller, drastically reducing the total travel distance of the grain.
They stopped giving the peas a turbulent, winding roller coaster ride and gave them a direct, straight-line flight.
Much gentler.
And the engineers combined this architectural efficiency with a very specific, optimized preconditioning process before the milling even starts.
Oh, the chemistry of it.
Right. The sources detail the chemistry of this. If you soak the raw grains in water for exactly 2 hours and then sun-dry them for 1 hour, it chemically and thermally loosens the natural adhesive bond between the outer husk and the inner cotyledon.
And that thermal loosening is crucial for machine lifespan and yield.
How so?
If the husk is already separated from the inner meat before it even hits the emery roller, the machine doesn't have to work nearly as hard.
Oh, that makes sense.
The factory requires less abrasive friction to dehusk the batch. Less abrasive friction required means less collateral damage to the valuable inner grain, which results in fewer shattered peas.
So it's easier on the machine and the product.
Yeah. When the researchers combined the optimized physical floor plan, the shorter travel distances, with this precise preconditioning chemistry, the total milling efficiency of the plant jumped from 75% to 80%.
A 5% increase in total yield just by logically moving machines closer together and soaking the peas properly.
It's massive.
It is a perfect demonstration that digital software and hardware upgrades must be deeply integrated with the physical space.
You can't ignore the real world.
You could invest millions in the most advanced acoustic yield governor, have it texting your phone every 5 minutes with perfect predictive data. But if your pneumatic pipes are 50 feet too long and your peas are constantly colliding with the walls of your building, you are still turning your profit into powder.
The modern factory is a deeply interconnected, holistic system.
It really is.
The biological reality of the raw seed, the architectural layout of the building, the violent mechanical kinetics of the emery roller, and the digital intelligence of the edge AI monitoring the vibrations, they all have to be perfectly calibrated to each other.
Right.
A failure in any one of those domains results in the destruction of food.
It is a phenomenal balancing act.
Truly.
Let's just take a breath and summarize the incredible journey we have been on today.
It's been a wild ride.
We started with a tiny, humble pigeon pea and a violently spinning abrasive carborundum roller. We uncovered the hidden, massive financial costs of the rotary kinetic deficit, how a fraction of a millimeter misalignment in a steel gap instantly destroys tons of human food.
Right.
We tracked the historical evolution of industrial maintenance, moving away from the old-school, expensive guesswork of preventative checklists, where factories were forced to shut down healthy machines just to inspect them.
The invisible ink?
Exactly. And we entered the data era, witnessing the rise of predictive maintenance and edge AI intelligence, where unassuming matte black sensors listen to the microscopic acoustic signature of degrading steel bearings, catching failures days before they happen.
Listening to the machine.
We saw how this automated monitoring saves massive amounts of electrical energy by tracking motor amperage. And through the philosophical lens of restorative engineering, we saw how technology restores human dignity by elevating workers from dangerous, mundane labor to a position of intelligent governance.
Getting hands out of the machine.
And finally, we saw how even the physical architecture and layout of the factory floor dictates the survival of the food we eat.
It really serves as a masterclass in how hidden, invisible systems govern the physical reality we interact with every single day.
It really does. I will certainly be looking at a simple bowl of Dal with a lot more respect for the kinetic journey it survived to get to me.
Absolutely.
But before we wrap up our deep dive, we always like to leave you with a final, lingering question to ponder, something to take with you based on the research.
And we have spent this time examining how acoustic governance can save a factory's productivity by giving a digital voice to degrading hardware.
Right.
The heavy machinery is screaming its wear and tear, and we finally built a piezoelectric sensor sensitive enough to hear it.
But consider the invisible systems in your own life.
Right. Think about the aging concrete infrastructure of the bridges you drive over on your commute. Or think about the microscopic degradation of your own physical joints and your own biology as you age.
What if everything degrading around us is making a sound, emitting a frequency, singing a distinct song of its own decay, and we simply haven't built the right sensor to listen to it yet? That is a profound thought to end on. From the microscopic fractures in industrial steel bearings to the wear and tear of the infrastructure we rely on, we want to warmly thank you for joining us on this deep dive into the source material. We hope it changes the way you view the engineered world and the food on your table. Keep your ears open and keep listening to the hidden frequencies of the world around you. We will catch you on the next one.